Alright, so today we are going to be continuing on our lesson in trig, and we are going to start with the function of sine, or the sine ratio in the triangles. So remember, we're dealing with right triangles, meaning they have that 90-degree angle. Keeping that in mind, you might remember this video might be a good thing to watch. It contains all the information you might need to know on trig. You can watch it on your own if you missed it in class. It's just a silly little video that gives trig in a new light. Alright, so yesterday we talked about the theta, the hypotenuse, opposite and adjacent legs. If you remember, the theta was just an unknown angle, so it was pretty much the x of angles, meaning just how most mathematicians use x instead for a variable in most cases, typically showing x, which is why we're always asking you to solve for x, being just a random number. Theta is likewise, so that when you see theta, you know you're dealing with angles. Right? So when we come to it, theta, being the Greek letter, is used to denote angles, while x can still be used to denote angles, but a lot of times you will see that theta instead for angles specifically. Alright? Kind of like the x of angles. Alright, so remember, the hypotenuse is as we have been over many times, it is the side that is directly opposite. So it's this side right here. Do I have a highlighter? So it's this side right here. Wee, squiggly line. It is the hypotenuse. So it is directly across from the 90 degrees, and it is also the longest side. The longest has an N. It's the longest side, and it's opposite the right angle. Now, what about the opposite leg? Well, in order to find the opposite leg, we first need a theta. So we need to put theta in one of the two locations. I'm going to choose the lower corner, even though it could be the top corner. It's just depending on where we are, what we are trying to find, and what we're given. Alright, so opposite leg is what we're dealing with right now. So the opposite leg, this is going to be the leg that is not touching the theta. So that means it's not this one and it's not this one. It is directly opposite. So it is not touching. In fact, it is equally away because it has one side and one angle in between it, and the theta. So that's another way you can think of it. It always has a side and angle between the theta, while the adjacent, well, adjacent just means that it is next to. Alright, so adjacent means next to. Like if you had a house next that was adjacent to, I don't know, somebody, the store, you would be next to the store. So you'd have the Walmart, or you'd have the store right here. Just, that looks more like a bank. There you go, store. And here's your house. Nice tall roof. Door. You are adjacent, meaning next to. So adjacent is always next to. So a little trick you can use to remember that is it's always, that's not what I wanted. That's the yellow. So a useful little trick is to always just highlight that the side between, or highlight the distance between the right angle and the theta. And if you do that, you will always have your adjacent. So that is always going to be next to the theta. Alright, so for instance, if I were to take the theta, I want to put that back. If I were to take the theta and move it up here instead, then my opposite would move to directly across. So again, it would be opposite, and then I would highlight the distance between the theta and the right angle, and that would give me my adjacent. Alright, so the adjacent is always going to be next to, while the opposite is always going to be directly across from. So it's going to be the furthest one away from the theta. Alright. So today we are covering sine, which you might remember from the Getting Tricky With It video, is the so it is the opposite over hypotenuse. So we have opposite here. So this being sine, this being opposite, and this being the hypotenuse. So it is the first part of that SOHCAHTOA that they were talking about. The SOHCAHTOA. So this being the sine function or the sine relation. So you have the sine of any angle, so we're using theta because that's what we use for angles, is going to be equal to the opposite divided by the hypotenuse. So if I have this right triangle, let's call it x, y, z, and I have my theta up here, then I would say that sine theta would be equal to the opposite over the hypotenuse. So that would be equal to, opposite would be z, over the hypotenuse would be y. So I say, all right, so there I have it. The sine of theta is equal to z over y, whatever those values are. Again, we're back to the regular alphabet, symbolizing just any unknown value. But maybe I do have a value. Maybe I have the value of, say 9, 12, and 15. Actually, those should be switched. 9, 15, and 12. You might recall this is one of those Pythagorean triples of 3, 4, 5, which do make right angles. So this is an actual triangle you could use. You could have. So you'd have that the sine of theta. Let's drag it up here. Actually, you know what? Let's have it in the bottom this time. So you have the sine of theta. So all right, the sine of theta. So that is going to be equal to the opposite over the hypotenuse every single time. So that's going to be equal to, well, my opposite is my 9 because it's directly across from the theta. It is the only side not touching the theta. Over the hypotenuse, again, directly across from the 90 degrees is 15. So at this point, we have set it up properly, even though that this could be simplified, because if we simplified it, that would just give us 3/5. Again, the opposite hypotenuse. Going straight back down to the original triangle. So we'd have that the sine of theta, whatever theta is, would be 3/5.